안녕하세요. Good morning. Morning. Yeah. 네. Good morning. 안녕하세요. Okay. Let me see. It's a little bit laggy, but I think we can give it a little time. All right. Welcome to week 10 of AI504. Sorry about that. All right. Yeah. Well, again, welcome to week 10 of AI504. So this week or today, we're going to talk about recurrent neural networks and sequence to sequence. But before we begin, I should tell you again that the the research that we're doing about using the AITA and how you are using it and how we are, gathering the recording, the interaction, all the interaction that you're having with the AITA, we are storing it, and also the survey. They're all for like research purposes, right? So we are asking you to participate in the survey, and probably for those who are like heavy users of the AITA, we're going to ask you to have an interview. But if you don't want to have an interview, that's fine. But we are going to ask a couple of you, or maybe like 5 or 10 of you, to just ask how the experience was, and what it was like to interact with the AITA and whatnot. And so those are all good. But if you don't want to, and I said that in the beginning, the AITA team, the TA team, the teaching team is going to planning to publish a paper about it. If everything goes well, I mean, hopefully we can publish a paper about it, because this will be very useful to those who are thinking about installing the same structure and the same AITA technology. And obviously, the school is going to expect us to turn in a report as well. So when we are doing it, if any of you are not comfortable with, sharing your stuff and, being published, and I mean, we're going to publish it anonymously, obviously. Your personal information will never be there. Your names or your student numbers, they're not going to be there at all. That's all just for us to keep track. And when we are going to publish the paper or submit a report to KAIST, the headquarter, none of your private information will be there. But if you're still not comfortable with, your interaction or your interview or whatever, like all those, if you're not comfortable, those material going into the publication or the school report, you can just tell us, and then we're going to exclude it in the end. So just letting you know that there's no repercussion, no penalty or whatever when you don't want your material or your interaction being used for publication or school reports. So just putting it out there. Just let us know if you're uncomfortable. But again, we're making sure that your personal information or any of that will not be in the report or in the publication. Okay, so let us begin with the RNN. Is it? Yeah, it's way faster than before. So we're going to talk about RNN and bidirectional. So 3 things about RNN. So vanilla RNN, which is the very basic form, and then bidirectional RNN, and some more advanced stuff such as gated recurrent units and LSTM. Then we're going to talk about sequence to sequence, or particularly machine translation, and then attention, and that will be it. So this will be kind of like building towards transformer, actually, because transformer came out after RNN plus attention. So naturally, historically, it's easier to follow this footstep. So RNN. So RNN is all about handling variable length sequences. And what we mean by variable length sequences, you can think about classification problems such as image to label and sentence to label. So image to label is, for example, we've learned CNN. So CNN expects, when you're building a CNN model, the model expects to accept or be fed the same sized image all the time. Like if you trained your model for 128 by 128 image resolution, then you're like implicitly kind of like premising that will be the same sized image will be fed into the model all the time. Even though like resonant or inception, that they can accept different size, different resolution images after training during inference. For example, if you've trained your resonant with 128 by 128 resolution image, you can test the model with 64 by 64 or 256 by 256. It still works, but usually you use the same resolution image during training and test at the same time. So your input size is fixed, as opposed to sentence to label, for example, like a sentiment analysis, where you are given a sentence and you're trying to classify whether it's a positive sentence or a negative sentence. The size of your sentence can vary. That is given. That is always the case. It could be a 5-word sentence. It could be a 10-word sentence. It could be a 20-word sentence. You don't know how long your sentence will be at the test time. So that's the problem. So handling variable length sequence, it could be whichever size. You have no idea. Right, so input size is fixed versus input size varies by sample. And the classical way of handling text, which is a variable length input, is usually counting. So for example, we have a sentence like this: I gave the ball to John, who gave it to Mary. And you simply count the number of times. Oh, I forgot to mute everybody. You simply count the number of times each unique word occurs in the sentence. So I occurred once, gave twice, yada yada yada, right? So this can be a vector. So like this. So you have the number of rows will be the same as the number of unique words in your English dictionary. So it could be 50,000 words here, or it could be 100,000 words here. It's up to what dictionary you use. So you have all the words in your dictionary, and you just simply indicate the number of times each word or each vocabulary occurred in this particular sentence. So it'll be mostly 0, and only like very few of them will be non-zero, such as ball twice, gave twice, and I once, the once. Actually, ball is once. This should be 1. And 2 twice, John, who, yeah, so, yeah. So only like 1, 2, 3, 6, 7, 8, 9, 10. Yeah, only 10 words will be 0. I mean, non-zero, and the remaining like 49,919 would be 0. So it's a very sparse vector. But the problem with this is that because it's a counting-based algorithm, there's no difference between the first one and the second one, which is I gave the ball to John, who gave it to Mary, and I gave the ball to Mary, who gave it to John. So these two sentences are completely different things. The meaning or the information contained in the sentence within the two sentences are completely different, but the end result is the same because it's just counting. So different meaning or different information, but same representation. So representing a piece of text or variable length input text with a counting-based algorithm is probably not the optimal way to do it. So before we get into the RNNs, so there are a lot of things that was discussed in the classical NLP. So when I say classical NLP, I usually mean the field of study or the particular NLP topics that were popular or like heavily studied before the deep learning era, which is like 2014, I would say. So before 2014, all these were like heavily studied like particular topics such as like syntax, semantic, discourse, pragmatic, part of speech tagging, parsing, so dependency parsing particularly, and named entity recognition, SRL, semantic role labeling, like all of them were very important, were heavily studied to understand natural language. People thought like these were like important techniques to understand a piece of text and be able to, like, for example, develop a chatbot, for example. Nowadays, they don't do it. Nowadays, building a chatbot is all about just dumping internet scale data into transformer and then just fine-tuning it with reinforcement learning with human feedback, RLHF, like how ChatGPT does it. So none of these are important anymore. Or are they? I mean, linguistically, they're still important, but when it comes to handling text and then developing a machine that can talk with humans, these don't really matter anymore, which is, I would say, a little bit unfortunate because, like, all the like decades of effort put into these studies were, turned out to be pretty much obsolete. I mean, not probably not 100%, but pretty much they're not used anymore, which is an irony. So it turns out that all you needed to build a talking machine was just a lot of data, a lot of GPU, and a lot of money, and that was it. Interesting. But, still, like, linguistically, they are interesting topics. And sometimes these are important in NLP. Sometimes you do want to recognize certain types of named entities, such as name of a person, like people's names or country names or regions or whatever, like, or products. Like, you want to extract those out of it. But these days they don't build a model that can do named entity recognition only. They just use ChatGPT to do this instead, right? Right. So moving on to the RNN, it's all about representing variable length input, and the formula is very simple actually. So this is it. HT equals F, which is a nonlinear activation function, which was originally a tanh. So HT equals F, and inside there's 3 learnable parameters, 1, 2, and 3. So WXT plus UHT minus 1 plus P. So what is H? H is the hidden variable. So it represents a current state of the RNN, at time step T, which is determined by the input to the machine, input to the RNN at current time step. So X is the input at Tth time step, and HT minus 1. So this is the hidden variable from the previous time step. So the current state is determined by the current input, previous state, and you just mix them up. So B is the bias. So you just mix them up. You just do a linear combination of the two. So this is a linear operation. This is just simply multiplying the input with a matrix, and multiplying the previous hidden state with the matrix plus the bias. So everything in here is linear. And then you just apply one nonlinear activation function, and that becomes your current hidden state. So that's it. So depicting it would look like this. Depicting this formula would look like this. So you start with a 0 vector, which is the very first, like prior, like the very first, like, initial hidden vector or hidden state, which is 0. And then you start putting things in, like x1, x2, and x3. And each time you put things, your h0 becomes h1, h2, and h3, and so on and so forth, right? So this is why you can use RNN to handle variable length input, because you are reusing the same trainable parameters, W, U, and B, the same trainable parameters all the time as you move forward in time step. So whether it's x3, x4, x5, x6, x10, x11, x100, x1000, it doesn't matter. You are always using the same set of parameters. Right? Yeah. So U is the one that transforms the previous hidden state to the current hidden state. And W is the one that transforms your input to your hidden step into your current hidden state. So they have a role. U handles the state, W handles the input. So you can imagine that if this is 128 dimension, and if this is 256 dimension, then you would be 128 by 128 matrix. W would be 256 by 128, right? Because you need all these to be of the same size. And particularly, they all need to be 128 in this case, because this is 128, right? So U and W could have a different size, could be different size matrices. So if you turn it 90 degrees rotation, if you rotate 90 degrees, then you can see what's actually happening. So you can think of this as a feed-forward neural network, because you can see this is layer 1, layer 2, layer 3, layer 4. It's just that new information is fed at each time step. So there's X1 coming in at first layer, or the second layer, X2 coming in at the third layer, X3 coming at the fourth layer, and that's it. So if you look at just this part, it's exactly like feed for FFN. It's just that there's new information coming in. So that's why we're using the same weights repeatedly. So that because we don't know how many inputs or how many X's will be given to us. If we knew beforehand, if we knew that it's like, oh, I know that all the time only 10 X's will be given to me, then you can use different weights, like weights here, weights here, weights here, weights here. We can use different weights. But it's that we can't expect all the time to be given 10 X's, which is not the case, because this is all about variable length input. So that is why we're using the same weights repeatedly. Right, so so I hope that everybody understands what's going on here. All you do is just, all you have is just 3 trainable parameters, and you just train them using backprop, right? Then you can do backprop, because there's some loss function, there's some end loss function here, which will be backpropagated through here, 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 and also here, 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 so that U, and W will be trained. And I'm omitting the bias. So how to use RNN? Where to use RNN? So first one, there are in large there are 3 main applications of RNN. So first one is sequence level classification regression. So it's sequence level, which means that you put all the things into the RNN. So for example, you put all the words or the entire sentence into the RNN, which happens to be, let's assume that this is a 10-word sentence. So you put all the words in your sentence, and at the end, after you've completed feeding all the words into your RNN, you do some classification, like whether this given sentence is a positive sentence or a negative sentence. Or it could be a regression, but the important thing is it's a sequence level task. So 1 RNN to encode input and 1 prediction at the end. So for example, it could be sentiment classification or topic classification, those things. The second one is token level classification regression. So the important thing is token level task. So as you can see here, you put one word, you put each word into the RNN, and for each hidden state, you have to make some class decisions, some such as classification, or in this particular case, you're doing a part of speech tagging. So this is a pronoun, movie is a noun, and yada yada yada, and at the end, play is a noun. So there are multiple predictions, and to be more accurate, the number of predictions is as many as the number of tokens. So if you have 10-word, if you're using a 10-word sentence, then you must do 10 classification. So part of speech tagging or language modeling, which is all the rave today. So you can see the difference between this one and this one, right? And then the third one is many-to-many. So it's a sequence to sequence. So in this case, we are using 2 RNNs, 1 RNN to encode input and another RNN to decode output or to generate output. So 1 RNN receives input, another RNN generates output. So there are 2 separate RNNs. And the representative task to use sequence to sequence is obviously translation or question answering, or in a more like old-fashioned way. Chatbot was also implemented using sequence to sequence, but not anymore. All right, so three, 1, 2, 3 main applications. So let's look at one by one. So sequence level classification. So we're going for sentiment classification. So given a sentence like this, is it a positive sentiment or a negative sentiment? So this movie is as impressive as a preschool Christmas play. So obviously it's a sarcastic sentence, and it's a negative sentence, right? So what happens one step at a time is, this is your first hidden state, and I mean there's H0, which is a zero vector. I'm just omitting that. So what you do is you have maybe I can just draw that. Right. So in the first step, you put your first word, which is this, and this is represented by a very sparse vector. So as I said, we could think of like 50,000 dimensional vector, which contains all the words in English dictionary. So the first one like is from A to Z, basically. There's A to Z. And somewhere in here inside, like this particular dimension could represent this. So we turn this to 1 and all the other 0. So it's just one hot vector, right? It's a one hot vector. Oh, I said here it's 1 million. Doesn't matter. It could be whatever, right? As long as you have all the words in English dictionary, then you're good to go. So you put one hot vector into your first hidden layer. So actually this should be plus U H0 plus B, like this, right? But since this is 0, this is gone, and I'm going to omit bias from now on, so this is gone as well. So you only have this. So this is the one hot vector, and you have the input transformation matrix. When let's assume that this is 128 dimensional vector. Then your W matrix should be 50,000. Oh, let's stick to this one. It should be 1 million by 128. So it's very long matrix, right? So that's how you get your first H1. And in the second time step, you have just movie. So you have a different one hot vector. You put that in, and now you have, well, I mean, the notation is a little bit different. Sorry about this. So this is W, this is U, but now we call this WH and WI, since this is the input, this is a hidden state, right? So this is what happens in the second time step without the bias, obviously, and so on and so forth. You put all the words like the movie, this movie is as impressive, yada, 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 and play. So you play at the end, and you have the final hidden state, H10, right? So you can see that this is all recursively defined because H10 depends on H9, and H9 depends on H8, H8 depends on H7, and yada, 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 and then H2 depends on H1, and H1 is H1. So that's how you can back propagate all the way back to H1. And all along the way, you're updating your WI and WH and the bias, right? So you have the final H10, which can be seen as a sentence representation vector. So before if you remember, before this was, we represented the sentence using a counting vector, right? Like this occurred once, like as occurred twice, and preschool occurred once. Like that was our way of representing a sentence. But now, instead of doing that, we just put everything, all the words, into the RNN, and now we can treat this final H10 as a sentence representation vector, because H10 has all the information. It has received all the words in the previous time steps repeatedly, so that you have built upon the words, and then now you have H10, which should theoretically hold all the information put into the model so far. So H10 is our sentence representation vector. So that's why we can put this into our logistic regression layer. So H10 times the output vector or the logistic vector, and then the sigmoid function, and then you have the outcome between 0 and 1. So 1 could be positive, 0 could be negative. So that's it. So you have the do we have the loss function? Well, yeah, sorry. So you should have a loss function somewhere here with the loss y and y prime, and then you're good to go. So you backpropagate, then you update WO and WI and W10. All right, so far so good. Any question? Any question before we move on to the language modeling? No? All right, then language modeling. So this is an example for the second type of application, which is the token level classification. So sorry, going all the way back. Yeah, for the token level classification task, I've used the part of speech tagging as an example here, but in our actual material, we're going to use language modeling because we are going to implement this in our practice and also in the project as well. So what is a language modeling? I mean, these days, ChatGPT and Claude and Gemini, they're all called a large language model, right? So if you just minus the large, then you're just using a language model. So language model, what is a language model? So language modeling is basically trying to calculate the probability or the likelihood of a given sentence. So for example, let's assume that you are given this sentence, this movie, the same sentence, as impressive as a preschool Christmas play. What is the probability of seeing this particular sentence? That's the question. The probability or the likelihood, and the probability, which should be so this is a probability, right? So the probability should be very, very small, because out of all the possible piece of text in the English language, what is the particular probability of this particular sentence? So the set of English sentence is probably infinite, right? Like there could be one element that is I am a boy. There could be another element, which is you are a girl. And another sentence, for example, like I'm going to school. You see what I mean, right? There are infinite number of elements in this particular set. And out of all of this, and there should be like a distribution, right? And out of all the set in this set, what is the probability of seeing this particular element in this set? And the probability should be like 0.0000000, like 1% or something. But then there is one, but there is one there should be sentences with probability larger than this one. For example, like I am a boy should have a larger probability than this one, because if you look at all the internet, then you should encounter this particular sentence more times, more frequently than this particular sentence. And there should be sentences with probability lower than this one. For example, even more complex, more longer sentences than which is less likely to encounter when you're surfing the internet, right? So you see what I mean by language modeling. So how do we even begin to calculate the probability of the sentence? So that's the question, and that's where language modeling comes in. So what you do is you first factorize this probability into multiple factors, basically. So like P of probability of this, P of the movie given this, P of is given this movie, like yada yada yada. You see what's happening here. It's basically you need this. So what is the probability of this? What is the probability of this given this? This given this, this given this, this given this, this given this. Basically, it's just so mathematically, these two are the same thing. They are equivalent. And all you need is just a method to calculate this. What is the current word's probability given all the previous words? So that's all you need. Traditionally, how people did it is by using something called bigram and trigram. So unigram is not, but bigram is basically you calculate a likelihood of a pair of words. So pair of words like this, pair of words like this, 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 and this. So basically, you just go through all the text, all the word, all the sentences in your training data, and then you simply just calculate this because you can count, right? You can just count how many times this occurs in your corpus, how many times this occurs in your corpus, how many times this occurs in your corpus, and it's yada yada yada, right? So you can calculate the probability of all the pairs of words. Then you can, instead of fully calculating the factorized version, you just put this away and put actually no. You can approximate the true probability into P this times P movie this times P is movie, oops, this, and so on and so forth. So you just approximate this high order dependency into just into just like a single order, like just bigram basically. And obviously this would turn into P of play. Oops, doesn't look good. P of play given Christmas. Right? So once you approximate this into this with this version, then you can directly use the bigram because you've calculated all the probabilities of this pair of all pairs of words, and you can just plug them in here and here and here. So this could be like 0. Like 0.02, 0.05, 0.001, and so on and so forth. And you multiply all of them together, and that would give you the approximate probability of this sentence, which would be really, really small. So you usually use a log likelihood rather than actual probability because the value is so small, it will underflow. So you'd rather use a log likelihood. And you can go even further. You can use trigram, obviously. So you can calculate how many times these three words occur in your corpus, in your training data, like these three, these three, these three, these three, and so on and so forth. Then you can, once you've calculated the probability of triples, then you can approximate this a little bit better because now you don't have to throw this away. And obviously the last one should have Christmas and preschool as well. So it's a little bit higher order, right? So you can use trigram. You can use quadgram, 5-gram, 6-gram, 7-gram. You can use so on and so forth. But then you have to calculate exponentially more number of entries in your dictionary, because if you're calculating just pair of words, all you need is just, for example, if your English dictionary size is 50,000, then you need 50,000 times 50,000 entries for your bigram. But if you're using trigram, you need 50,000 to the power of 3 to calculate all the triples of words. If you're using 4-gram, then you need 50,000 to the power of 4 and to the power of 5, which is exponentially increasing. So sooner or later, it just doesn't work. It becomes too sparse. So people just stick to bigram or trigram. But that was the old way of doing it. And now we have RNN. Theoretically, we can model the full probability of this because you can just put all the words, all the previous words into your RNN and just simply predict the next word. And that's it. So this theoretically, you can now model a full language model with RNN. So how do we do it? How do we go about it? So you put each word into your RNN, and each time, instead of predicting the part of speech, like this is pronoun, this is noun, we don't do that. Now what you do is you predict the next word, and the next word, and the next word. And when it's the final time step, you predict the end of sentence, which is a special symbol that represents the end, basically the end of sentence, right? It indicates the end of the sentence. So when you put this, your model should be predicting movie. And when you put this movie, your model should be predicting is. And when you put this movie is as like here, then your model should be predicting play. And when you put all the sentences, all the words in your sentence, then it should be predicting the end of sentence. So this is how you do language modeling with RNN. So the loss function is pretty simple. you have your each time step, each hidden state at each time step. So you put that into your softmax, where the WW, the matrix inside your softmax, should be what? It should be 128 times 1 million, assuming that there are 1 million words, 1 million unique words in your English dictionary. So you're basically in here you were converting 1 million size vector into 128 size 128 dimensional vector, the hidden state. But now the output here, you're returning the hidden state back to the output space, which is the English vocabulary size. So once you have that, you will have a one hot vector here. So you would have like a one hot, actually not one hot vector. You should have like a 1 million size vector where each, let's draw it actually. So, and this should be 1 million, and this should be A and Z here, and somewhere inside there should be this, like somewhere inside should be a word movie, and you want the probability of movie to be the highest, as opposed to like you want all the others to be zero, like zero, and only movie to be one, but that's very unlikely. So it would be like 0.0001, 0.001, and movie should be like 0.5, hopefully, or 0.6, right? So that would be your y1 hat. So this 1 million size vector would be your y1 hat. And obviously your y1, the true y1, is actually what? It should be x2, the next word. So y1 is equal to x2. That's how you get your loss function. And loss function usually is just negative log likelihood, right? It's just negative log likelihood. And you have 10 loss 1, loss 2, loss 3, all the way to loss 10. So you have 10 loss terms for a single sentence. And the number of loss terms is equal to the number of words in your sentence, right? So given just one sentence, you update your model 10 times, basically. Or actually, you can do that, or you can just sum them up, or you average them, and then you get just one update as well. Anyway, so you can see how this RNN is becoming a language model, because once you've trained your model in this way, then you can feed, for example, you can feed this movie and then calculate what is the likelihood, or what is the probability of seeing the next word, which is. Like when you put this movie into your RNN, then you can poke at H2. You can convert this H2 into a softmax like this, then calculate what is the probability of a particular word is. Question, I think there could be many possible words right after this. Yeah, sure. While there are significantly fewer possible words after play, can this model handle this difference? If you train your RNN with so many sentences, basically just, like all the Wikipedia sentences, then it would recognize the difference between when after this there could be many different words, but after play there could be only a few words. It will know, because if this model just reads all the words, all the sentences in Wikipedia, it would understand the patterns in English in the English language. So you don't have to worry about that. So only valid result can be observed after some words are only valid. I don't know. I'm not sure what you mean by valid. You mean valid in terms of syntax, like grammar, or valid in terms of semantics, or what? I mean, which one? Syntax. Sure, yeah. The model is very likely to generate or produce syntactically correct sentences. If you've trained this model with syntactically correct text, but it's not guaranteed. There's always the problem of hallucination, right? So nothing is guaranteed with a generative model. Hopefully that answers your question. Question, if there are 10 loss functions, then each of their effects on decreasing loss become what? Then each of their effects on decreasing loss become less than just one total loss function, such as image classification. I'm curious the difference between multiple and single loss function and how they work. Uh, Actually, they all serve different. They all have different functionality because loss one only backpropagates once, but loss 10 backpropagates 10 time steps, like here, 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 here. Like, you see what I mean. So loss one should have a stronger effect, so to speak. I'm not sure if it's a accurate description, as opposed to loss 10, because loss 10 backpropagates 10 times. So as you backpropagate more times, the influence of your gradient or the influence of your loss will be diminished because of gradient vanishing problem or the gradient exploding problem on the other end. So they have like different effects. Like loss 1 and loss 10 have different effects. And if you use 10 losses, they would have they would, serve different purposes basically, as opposed to having as opposed to like image classification where you have just one loss at the end, which comes from the top, right? As opposed to loss one, loss two, loss three, which comes from the intermediate steps. So it's a little bit different. Cool. So this was language modeling. And we come to now bidirectional RNN, which is a little bit of like an extra. So bidirectional RNN encodes a sequence in two directions. So the forward direction and the backward direction. So you can see the arrows going forward and arrows going backwards. So how you do it? You just simply, for this forward version, you put the sentence in a regular order, like this movie. But in the backward, you put the sentence in a backwards order. Play Christmas preschool as like Maria and movie this. So that's it. So you put once in a regular direction, once in a backwards direction. So you have forward representation and the backward representation. So the forward representation would be this. The backward representation would be this. And once you have these two representations, you just simply concatenate them and then do whatever you want. It could be classification, it could be whatever, right? It could be translation and so on and so forth. So this was bidirectional RNN was a thing for a very brief moment, for a very brief like period of time between like 2014, 2015, and then attention came out. So it just people no longer use it. So the limitation of RNN. So the problem is, I mean, it's all good because now you can have infinite horizon window. Theoretically, you can put as many words into this RNN as you want. Like it could be, you could put 100 words, 1,000 words, 10,000 words. Like theoretically, you could put as many words into this model. But there are limitations. So the first one is called vanishing gradients. So vanishing gradient is it also applies to feed-forward network. When you use too many layers in your feed-forward network, for example, like 10,000 layers or 100,000 layers, your gradient will no longer exist after backpropagating for so many layers. So if you have 1, 2, 3, 4, 5, like all the way to like this is like 100,000 layers. Before the RN, so before the birth of ResNet, before the residual connection, like even like 100 layers didn't work. Let's just forget about 100,000. Like even 100 layers wouldn't work without the residual connection. So let's think about that. So what happens in a 100-layer feed-forward network is that there's loss function at the top. And then this loss function, this loss value will be back propagated all the way down to the first layer. And each time you're back propagating, you are basically just doing like a bunch of like matrix multiplications. And bunch of matrix multiplications, if it's not stable, it'll quickly go to 0, or it will quickly go to, do we have vanishing explosion? Yeah, exploding. So it's either it'll quickly go to 0 or it'll quickly go to like very hard, very large value, or even infinity, because you're doing matrix multiplications at each single steps, each single layer when you're doing back propagation all the way down to. So if you have 100 layers, it means that you're multiplying your matrices like 100 times at least. So that's the problem with the vanishing gradient. So vanishing gradient, which means that your lower layers will never update because the gradient value will be 0, basically. So long sequence means long backpropagation in chain. So the same goes with RNN. If you use RNN, it's just having side input at each time step, right? So 100, if you put 100 words into your RNN, it means that there will be H100 all the way to H1, and the vanishing gradient still exists. And which also means that input from a distant past is forgotten. For example, if you put too many words into your RNN, then the words in the initial time steps, like in the very beginning, they will no longer influence the final hidden layer, the H100. So, for example, let me erase all this. If your given sentence is like this, like Jane walked into the room, John walked into, it was late in the day, Jane said hi to. So what should come here in this next word? Then the answer is obviously John, because Jane and John are in the same room. But because this is such a long, you can imagine like there can be like many more sentences in between. And then at the last time step, you ask what should come in this slot, what word should come in this slot. And in order to answer this question, the RNN has to remember this information, which is like way in the past, which is not a trivial task. So again, like this is also a problem. And how do we remedy these problems? How to remedy this? So there are some tricks, such as like initializing your weight matrices to identity, which is kind of like, copying the spirit of residual connection and using ReLU and whatnot. Like there were some tricks to tackle this problem, but none of them really worked. And even if you use this remedy, there's still exploding gradient problem as well. So, I mean, but for exploding gradient, the popular remedy is just gradient clipping, which is still used these days. So, but these two are problematic. And that's where we have gated recurrent units, GRU and LSTM. So GRU and LSTM particularly were designed to handle these problems. So we'll start with GRU. I mean, LSTM came way before GRU. I think LSTM came in the 90s, if I remember correctly, and GRU came in 2014 by Professor Kyung-Hyun Cho and Yoshio Benjun, those groups. So even though GRU came in later than LSTM, it's actually simpler. Architecturally, it's simpler, and LSTM can be seen as just more advanced GRU. So it's easier to talk about GRU first and then move on to LSTM. So what is GRU? GRU is just using more complex hidden unit computation in recurrence. So it's called gated for a reason, because it uses two gates. So it uses gates to keep around memories to capture long distance dependencies, and it also allows error messages to flow at different strengths. So you'll see what you mean. Basically, GRU wants to tackle these problems, so it uses something called gates to control the information flow. So there are two gates. There's an update gate, and then there's reset gate. As opposed to the vanilla RNN, which is your hidden state is determined by your previous hidden state and your current input, and now U and W has become WHX and WHH. It's different notations. So this is vanilla RNN. As opposed to the vanilla RNN, you have update gate and reset gate. And the update gate is calculated like this, and the reset gate is calculated like this, and it looks very similar to this. So you have W and U, and W and U, and U handles the hidden state, W handles the input. So it's the same here. It's just that W here, WZ and UZ are used for the update gate. WR and UR are used for the reset gate. But the architecture is the same. I mean, the mathematical formula is the same. And sigma is a sigmoid function. So the reason that we're using the sigmoid function is because this is a gate, and the gate should be either open or closed. So if this output is 0, it means the gate is closed. If this output is 1, then it means the gate is open. And the same goes with reset gate. So you can see the similarity here, right? As also here. So once you have the update gate and the reset gate, what you do is you calculate the new memory content, which is just intermediate memory, which is H tilde. So you take the reset gate, and so let's just forget about this one for just a minute. Let's just forget about this one. Then it's just U times the hidden state W times the input, and with different activation function. Now you're using 10H. But what happens is you're multiplying this reset gate to your hidden state or transformed hidden state, and then you add that to your transformed input, put it through 10H, and then you get the H tilde. So what happens here is if the reset gate or the reset gate unit is close to zero, if this is zero, what would happen? If this is zero, then this will go to zero, which means your H tilde will only contain the current input. So that is why reset gate kind of resets the state, because it controls how much your previous hidden state will influence your current H tilde, which is the intermediate hidden state. After you get the H tilde, you finally calculate HT, which is just a weighted sum between your previous HT minus 1 and your new H tilde. And this is where your update gate is used, Z and Z. So you can see it's a convex sum between this guy and this guy, because Z is either 0, Z has a value between 0 or 1. So what happens here? If update gate is 1, what would happen? It means that this guy will go away, and only this will survive, which means that it's just your new hidden state is a copy paste from your previous hidden state. And if Z is 0, then this will go away, and only this will survive, which means that your new hidden state is a copy paste of your intermediate H tilde, which is determined by this formula. So this is how reset gate and update gate and reset gate influence. They play their roles in calculating the final hidden state. So it's a little bit more involved than vanilla RNN, right? Vanilla RNN is just one step, but now you have to calculate. Now you have to calculate this one, and this one, and then this one. So it's 4-step process. But you can optimize the computation because they look so similar to each other. But theoretically, it's a 4-step process. Right. So if you put it in a picture, it would look like this. So your new HT will depend on HT tilde and HT minus 1, and the final one will be controlled by Z, which is here, and there's also R controlling this content here, and yada yada. So it's just 4 lines of code as opposed to a single line code in vanilla RNN. All right. Any question? So, theoretically, hopefully, if for example, if your current input xt is not really relevant, it's like the model can, if the RGRU can consider the current input xt to be useless, then the update gate can be 0. Update gate can be 1, so that this component goes away, and it just tries to retain the previous information as much as possible, right? On the other end, if previous HT minus 1 is, it seems useless, like if the current input is so important, then the update gate can be close to like 0, and then this will survive. But obviously, reset gate also will play its role. Like if the model thinks XT is so important, then this will go away. So reset gate should be 0, and update gate should be also 0. Right. So you can see how reset gate and update gate plays a different role when it comes to controlling the information flow throughout the time steps of the RNN. All right, so moving on then. So LSTM is just GRU plus one more gate, which is 3 gates now. So they have different names: input gate, forget gate, output gate, but it's basically like very similar process. So there are 3 gates, all with sigmoid function, and then there's intermediate, something called memory cell. So the LSTM calls this a memory cell instead of H tilde, I guess. So there's intermediate memory cell, and then the final memory cell, which is forget times CT minus 1, input times C tilde, and then the final hidden state is this. So if you played around with LSTM implementation in PyTorch or TensorFlow, as opposed to GRU has one output, meaning it has just one output, which is HT. But LSTM has two outputs, CT and HT. And I'm not sure why. I guess the designer of LSTM thought they would have different purposes. I forgot what it was. It's such a long time ago, but you'll see what I mean when you look at the PyTorch code of LSTM. Right. Finally, sequence to sequence. Oh, actually, not finally. There's one more thing about attention. So sequence to sequence, we've looked at sentence level classification, the sentiment classification. Then we looked at token level classification, which is language modeling. And now we have sequence to sequence, where we use two separate RNNs. So given variable length input and also variable length output, both input and output are variable length sequences. So this is where sequence to sequence comes in. And it's especially well suited for machine translation, question answering, and chatbot. Because, for example, when you think of machine translation, there's no guarantee that the input language and the output language are of the same length. If you do like English-French translation, there's no guarantee that the English sentence and the French sentence will be of the same size or have the same number of words, right? So naturally, we need two RNNs, obviously. So if we think about, okay, so French to English, French in I am a student is je suis étudiant, I guess. Je suis étudiant plus the termination symbol, so 4 words. But the corresponding English sentence is I am a student, EOS. So there are 5 words, 1, 2, 3, 4, 5, right? As opposed to 4 words. So as I said, no guarantee between the input and output regarding the size or regarding the number of words. So that is why you need 2 separate RNNs. So what is the output of encoder? You can ask, what is the output? You can obviously you put the French sentence into the encoder, and obviously the decoder should generate or output the English sentence. But what is the output of the encoder here, and what is the input of the decoder here? That's the natural question that we should answer. And encoder, so the encoder's output, there is no particular, I mean, you don't actually output anything except for the last one, H4. So H4 is the French sentence representation vector. That's how we saw it in the sentiment classification task, right? The final hidden state is supposed to represent all the words given so far. So H4 is the French sentence representation vector, and nothing comes out on this side, right? Nothing comes out on this side. Input to the decoder, input to the decoding RNN is the ground truth. So start I am a student should be put into the decoder, and decoder should output the next word, I am a student AOS. So if you just look at decoder only, it kind of looks like a language model, right? But the language model generates any arbitrary language. But here, we don't want to generate any arbitrary language. We want to generate a language or English sentence that corresponds to the given French sentence input, right? So that's where this plug-in, this connection comes in. So you can think of this as a language model, but with a condition. It's a conditional language model where the condition comes in from your encoder, French encoder. So your H4, the representation vector, becomes the very first state in your decoder. Here, the H0 is 0 vector, right? But here, the S0 is the same as H4. So that this becomes a conditional language model, right? So the training phase, decoder input is the ground truth. Sorry about this ground truth tokens. And you apply the simple just negative log likelihood. So you have the loss function 1, 2, 3, 4, 5 loss functions, and you simply just do the backprop, and that's it, right? So that's what happens in the training phase. You have all the inputs from the from the French side, and you have all the inputs from the English side. You put inputs to the both encoder and decoder, and you have the output here, which can act as a loss terms, and then you just do a backprop, and that's it. So you're good to go, right? Which is the training phase. But in the test phase, you don't have the ground truth input. You don't know what to put into this part, because in the test phase, you don't know what the corresponding English sentence of this French sentence is, right? So this is where you actually do autoregressive prediction. So you put, this part is given to you because you know what you want to translate, right? So this condition or this French input is given to you, to the model. So you put all the words into your encoder, and then you have H4 ready. And once you have the H4 or S0, which is the same thing, you start with the start token. So start token, you at least know that you want to start the decoding process or the translation process, right? So you put the start token, and then you see what comes out on this side. And hopefully, they should be I, right? And then once you have I, oh, we don't have it. Once you have I, you put I here. So in the time step 2, you put start NI to your decoder. I mean, your S0 will be the same, right? So you put start NI into your decoder, and hopefully this will come out as M. And then you put start IM, and then start IM, then student, right? And start IM, student. Hopefully you'll get EOS out of it. And then that concludes your translation. So the training phase and the testing phase are two different things. Training phase, you have all the input, and then you just simply do a backprop. But in the test phase, you still do have the input because you know what you want to translate, but you don't have the output. So you have to guess one at a time. You have to predict one word at a time and then do autoregressive prediction. And how many times do you have to autoregressively predict until you get the EOS out? So it all depends on, it is determined by the model. Right. So this is sequence to sequence. Questions? So any questions so far before we go into the attention? All right. If not, then we move on to the final topic of today. Attention. So attention model came out in 2014 at the same, like right after the GRU was proposed. I mean, GRU based. So GRU was proposed to do a machine translation in a purely neural fashion. Like before GRU came out, the machine translation was mostly statistic, and it heavily depended on like parsing and grammar and like all of that, the classical NLP techniques. But what GRU did, so let's go all the way back to GRU. This particular paper here, what GRU did was, let's do a translation, machine translation, in a purely neural fashion using RNN, like without all the dependency parsing and all that. Let's just use RNN, 2 RNNs, and then do machine translation. So that was the revolution. That was a revolutionary paper. And right after, not right after, but after GRU came out, certainly it had limitations. All the limitations like this and other limitations as well. So what the authors of attention did is, let's use something called attention to improve the performance of GRU-based machine translation or neural machine translation, NMT. And the philosophy or the core idea is, let's use hidden layers from all time steps. Like let's use all hidden states from all time steps to do translation. So what we mean by is using all hidden states, meaning before when we were doing sentiment classification, H10 was H10 was considered to be the sentence representation vector, right? So we only use the H10 to do a binary classification. But instead of doing that, how about we pull information from all hidden states, from all time steps, and then do classification? So what we do is we do a weighted sum of all the H1, H2, H10, weighted sum, and then get something called a context vector. So you can see the context vector C is just weighted sum of all the H's. And there's one more constraint, which is alphas, the weights, should sum to 1 so that the magnitude of C doesn't explode. If you just simply weight sum everything, then the magnitude of the C vector could, like, it could be arbitrarily high. So we don't want that. We want to keep the size of the C vector to a reasonable size, right? So that's why we do a convex sum instead. So all the alphas should sum to 1. And then once we have the convex context vector, then we can do any classification test that we want, right? So attention, what is it good for besides improved performance? I mean, obviously you can see why it would improve performance, because instead of using only the last time step H10, you use all time steps, so it is less likely to, like, one of the problems RNN was the words in the beginning, words in the initial time steps, they are easily forgotten. But if you use all time steps from all, I mean, if you use hidden states from all time steps, that doesn't happen anymore. If the initial words were important, then these alpha values would be high. So like now you're using all information from all time steps. So besides the improved performance, what is it good for? Another thing that is good with you, another benefit that attention brings is that it gives you a, we can tell which word was, kind of like interpretability, basically, because alphas now denote a usefulness from each word or each time step. Now we can tell which word was used the most or the least to the outcome. Because alphas are supposed to sum to 1. You can think of this, like if this was like 0.3, 0.4, and 0.05, and 0.01, then you can think of this as, oh, in this particular prediction, these initial words were way more important than the later words. So there's a bit of a interpretability coming in as a bonus. So so far this is all good, but how do we generate, or how do we determine the alpha weights? And how do we keep them sum to 1? So first of all the attention alphas are generated using a separate MLP or separate function called attention function. So let's assume that we have a separate MLP, multi-layer perceptron, that looks like this. So it is simply just a multi-layer perceptron with a single hidden layer. So there's input, there's hidden layer, then there's output, and there's no sigmoid or activation function on the output. The output ranges -infinity to the positive infinity. And we're going to call this function AX, the attention function X, attention function A. So what you do with this AX is you take all the H's from different time steps to AH1, AH2, AH9, AH10. Then the output Y1 to Y10 should have the range between, oh, this looks bad, -infinity to positive infinity, -infinity to positive infinity, all the way to the end. So this is just simply a regression function. It's a regression function. It's a regression function. And your output Y's, they don't sum to 1. But when you put all the Y's into the softmax function, then now it sums to 1. So that's how you do it. So you take all the Y's and then you put it into softmax and you get all the alphas, and alphas now will sum to 1. So that's how you get this value here, these values here. So there's a separate MLP, separate attention function that gives you the alphas. And they're all trained end to end. Because if you see here, your context vector is derived by a weighted sum of all the H's, and these alphas play a role, and these alphas are determined by the MLP function, the attention function. So when you do a backprop, they are actually going this way and also this way. So the RNN part and the attention function part, they're all updated at the same time. So attention function meaning like these parameters, they're updated end to end. Do these MLP share weight? You're using only single MLP, A, for all time steps to calculate alphas. But the MLP and the RNN, they don't share weights. Okay, cool. Right, so softmax function ensures alpha I sum to 1. And now, we've covered the basic concept of attention, let's see how it is used in the sequence to sequence where this paper was all about. So this paper used attention in a sequence to sequence manner. So let's see how it was used. This is how you did sequence-based neural machine translation, right? You put all the French words in, and then you take the H4 as a French sentence representation vector. You plug that into the decoder as S0, and then you start decoding, right? So that was what happened before. But now we're using attention. This is what happens. So instead of having H4 and plugging that in, what you do instead is at each time step, well, particularly, let's assume that you've already had start in, and then there's some y1, and then this is the second time step. So when you're doing a second time step prediction, you take all the h's, do a sum to a convex sum. You do a convex sum, and then you get something called context vector, right? Just like how we had a context vector here, doing a weighted sum of all the h's, you have context vector for the particular second time step. So there's C2, because now we're at the second time step, right? You do a convex sum, you get C2, context vector 2, and then you have S1 from the previous time step, Y1, the current input, and then Y1 being this, right? So you have the current input, previous time step, and the current context vector. You have all three to determine S2, and then you get the final output, right? So instead of having previous S1 and current input, and then those derive S2, and then you having the output, instead of doing that, you have three components, S1, C2, and Y1. And then you get S2, and then you get the final prediction. So mathematically speaking, it looks like this. At each time step, so this particular example was we were in the second time step, but there was actually C1. There was C1. And if there's S3, then there should be C3, which means that each time step, you are doing a weight sum of all the H's using different weight combinations. So the alphas that you use in S1 or the first time step, and the alphas that you use in the second time step and the third time step, they all differ. They're all different, right? So in time step I, each yi is predicted based on Si. So each yi is predicted based on Si, S2 in this example. And each Si is derived from three things: previous S, current input, or in this particular, current input is the previous out, because this is sentence. This is a translation, right? So previous output, previous hidden state or previous S, current input, and current context vector, three components. So you put this like here. So your RNN, so this is RNN, right? So your new hidden state is determined by your previous hidden state and your current inputs, which is current input itself and the context vector. Then you multiply the W to this concatenation of these two. So you get S1. And C1 is derived from previous hidden state and all the hidden states from your encoder. So all the hidden state from your encoder, H1, H2, H3, H4, and this guy. So when you're determining these alpha 1, alpha 2, alpha 3, alpha 4, you're not just using H's, but you're also using S's, the S1 or the previous S. So how it happens is, look at here, you can do, you should start from here. Your attention function, before your attention function only used your attention function only used H's, right? Only used H's. But here now, because we're doing a sequence to sequence, your attention function receives your input hidden state and your previous decoder hidden state. So this is the encoder hidden state, this is the decoder hidden state, and decoder hidden state is fixed. Decoder hidden state is fixed. You can see it's all fixed, right? But your encoder hidden state, you use different encoder hidden state, H1, H3, H1, H1. So you use the same attention function multiple times while fixing this, while changing these. Then you put it into softmax, and then you get alpha i's. So that is why I said, when you're calculating context vector, so when you're calculating the alphas in the first time step, alphas in the second time step, alphas in the third time step, they all differ, because you can see that because S is used when calculating the alphas. So when it's the first time step, it should be S1 going in. When it's the second time step, S2 should go in. When it's third time step, S3 should go in, right? So that's how you get the alphas from each time step. And then once you have the alphas, you have the sum, you have the weight sum, and that's how you derive C1, Ci, and then you put it into here, and then you derive Si, and then you put Si here, you get the final this prediction here. So it's a little bit more involved, as opposed to vanilla sequence to sequence, where you have just H4 plugging into the decoder. That's way easier. But now you're using weighted sum of h's from different weighted sum of h's in each time step. So it's a little bit more involved. But if you just follow this step, then it'll be not too easy, not too difficult to understand. So this is the final slide of today. What really happens when you do a translation using this architecture, the attention pattern looks like this. So I think this is English to French translation. So the encoder accepts the English sentence here, and the decoder should predict one French word at a time, right? So what happens, for example, what happens is that in each time step, in each French word prediction, different combinations of English words or English hidden state, the encoder hidden state, is used. So when the model is trying to predict the French word destruction, you can see how H's like H1, H2, H3, all the way to like H15 or whatever, they are combined using different weights. And specifically, this particular H1 was heavily used. Like alpha 1 value was like probably 0.8, and alpha 2 was like 0.05, alpha 3 was like 0.02, something like that, right? So, and it makes sense because in order to predict the French word destruction, it should be natural to look at or use the English word destruction most heavily, right? And goes with the Syria here. When the decoder was predicting the word Syria, the combination of encoder hidden states was like this, and like this. And particularly, this particular word or this particular time step was heavily used, which corresponds to Syria. So again, making sense. And since English and French are both Latin-rooted language, their alignment works out pretty well. Like it's pretty much diagonal, right? So if we had like English to Korean translation, it would be all over, everywhere. All right, so this is it, and hopefully everybody followed along. So the sequence to sequence and attention, those two things are very important concepts because transformer will be using attention and sequence again. So hopefully everybody has the clear picture in their mind. Any question before we end the class today? So this practice session on this Thursday, you will be implementing the sequence and attention. So please attend. You don't really understand something unless you like create it, unless you like code it and create it yourself, and then see how it goes. All right, I'm gonna wait 10 more seconds just in case someone's typing stuff. All right, I guess no questions. And thank you for attending the class today, and I'll see you guys next week. Bye-bye. Thank you. 네, 감사합니다. Thank you.